Okay, so this lecture we're going to talk about distributed data processing. So just a little bit of a warm-up. So in most areas of science, or many areas of science, I think most possibly an exaggeration there, data is doubling every year. So you get increasing amounts of data that you have to process in different ways. We're even getting to the petabyte scale, so the Large Hadron Collider producing 30 petabytes annually, and this data needs to be processed to identify which particles are colliding with which, whether we found a new particle and all the rest of it. So the petabyte scale is absolutely vast. It's like 1 billion books you've got to process in order to do the work in this kind of science. And heading towards the exabyte scale in some areas. So genomics as well is probably pretty big in terms of data. And neuroscience, as I'll say, is not so big at the moment, but is set to get bigger and bigger. So, and we're heading towards the exabyte scale, and all words ever spoken by human beings ever is estimated to be 5 exabytes. So vast amounts of data needs to be processed in science. So yeah, I said health, genomics, particle physics, astronomy, some of the key areas in science that are needing deep big data processing. And in my own area of interest is processing data from the brain. And so you probably come across functional magnetic resonance imaging, where you're, put people in a dirty great magnet and sort of read sort of average activity of different areas of their brains. Well, in that case, you're dealing with approximately 1,000 data points, and these data points change once every 5 seconds, let's say. But with optogenetics, you're getting much more data coming out of the brain potentially. So with optogenetics, you're modifying the neuron so that when it fires or when its voltage changes, it emits a bit of light, and using a special microscope, you can read off exactly which neurons are firing in the brain. And so this is a zebrafish larvae, and this is a great subject for this because it's got a transparent brain, so it's easy to use to measure the activity deep within the brain because it's just transparent. So now we're getting to the stage at which we can read maybe 100,000 neurons at 1 hertz in a zebrafish larvae, so this is 100,000 data points per second. And as we get better at doing this on mammals, we're likely to get much more data. Now, the human brain has 100 billion neurons, and they fire at maybe 5 hertz, something like that. So if we could actually access all of the data in all of the neurons in the human brain, we'd potentially have an absolutely vast amount of data, and we'd have a really challenging task trying to process this data, understand this data. And so my own interest is in using machine learning and big data approaches to identify patterns in large amounts of brain data. That's the idea. So big data in neuroscience, not yet a problem, but soon to be a problem, I think. Big data and artificial intelligence has suddenly become a massive sort of trendy topic, all this kind of relationship between big data and artificial intelligence. I think it's a kind of combination of the ability to process large amounts of data using cloud computing, as I'll explain, combined with what's called sort of deep learning, where you're using like a neural network with lots of different layers. And so this company, DeepMind, owned by Google, has done a lot of impressive work, most recently with Go. And I think I mentioned they work on learning Atari games in the lecture on online games. But this is another example of big data and artificial intelligence. So this is IBM Watson, I think one in 2012, something like that. So it's an absolutely massive system. I mean, it's, even 5 years ago, whatever, it was a big system. You've got, 3,000 processor threads, 16 terabytes of RAM, and this thing can hoover up, 500 gigabytes or 1 million books per second. So it's an enormous natural language processing engine, and it sort of uses these sort of multiple different approaches working in parallel and then combines the answer. And what this thing was originally built to do was to win at this quiz game Jeopardy. So it's basically a quiz game. You're asking it general knowledge questions, and people compete to press the buzzer quickly and answer those questions. And Jeopardy's got a slightly funny way around. It sort of asks, it tells you the answer, and you've got to ask the question or something like that. But it's basically a quiz game. So IBM threw a ton of cash at this and built this really big, impressive natural language processing engine that sort of read Wikipedia, read every encyclopedia that's out there, read everything on the web it could find. And it beat these guys at Jeopardy. And there's the 2 humans looking slightly sad, and there's Jeopardy winning $77,000. So there's some good papers on this, and it's worth a look if you're interested in this stuff. And more recently, they've decided to try and make some money out of this system they spent so much time and effort creating. So they've got a big thing about cognitive processing now, which is basically using the same sort of thing, hoovering up vast amounts of data from a particular domain, and then being able to answer questions and intelligently process that data. So, I mean, they turned me down for a job last year on, working on this kind of stuff. But the idea was to do like healthcare, for example. It could like read all the medical textbooks and then be able to answer questions about the diseases or diagnose diseases and this kind of stuff, or any kind of problem that requires a lot of knowledge. They're hoping this kind of architecture will be the next big thing. Now, in government and business, it's also extremely useful and extremely important to be able to store and process vast amounts of data. So, if you're running a company, you want to identify patterns of customer behavior, suggest products, etc. I'm sure you've all seen your targeted adverts appearing on the edge of your email if you use a free email account. Google searches, again, they're trying to, predict, accurately what you're looking for, but also try and target ads based upon, their model of who you are and what you do. Facebook uses stuff all the time to optimize your timeline. And, there's lots of ways in which you could presumably optimize things like healthcare, police services, tons of things you could do by processing the data in more complex ways. So there's an example which I've put on the web page from Walmart trying to do this and being a little bit controversial about it. So the general picture is that when a woman gets pregnant and the family has a new child, for the first child particularly, their consumption patterns are very flexible. They're in a state of flux. Most of the time, most of us just go to the same shops, buy the same stuff, and it's very hard for a rival supermarket to lure us away from our established habits. We don't check out the prices every week and go to the best place. We just build up habits and stick to those habits. But when you have a new baby in a family, everything changes. There's you're buying a whole new different set of stuff. You've got a whole new set of habits. You're a vulnerable consumer if you want to be lured away by another supermarket. So what Walmart wanted to do is identify whether a woman was pregnant based upon her buying habits. And they had a guy there, and he built up this really, really nice, accurate model by analyzing all the purchasing patterns, and doing probably some machine learning statistics or whatever on it. And he found out that in early stage pregnancy, women, I think, tend to buy less perfume products, like perfume-free tissues and wipes and all this kind of stuff. So he found a very nice marker for early stage pregnancy in the buying habits of the Walmart customers, and so they could then target their marketing to people who bought those kinds of products because they were fairly sure that they were in an early stage of pregnancy. So there was lots of controversy surrounded because they often were sending the targeted adverts before the woman had necessarily announced the pregnancy to the family and all this kind of stuff. But it's a nice example of picking up patterns in consumer behavior and using them to target customers in a potentially effective way, although this is possibly too controversial to actually use. So, there's this MGI report I've also put on the course website talking about 300 billion potential annual rev value to the US healthcare. So if you can optimize things, machine learning and data processing, then, you can save a lot of money. You can get rid of a lot of civil servants, if you do all this stuff in the European Public Sector Administration, and possibly 60% increase in retailers' operating margins. So human processing of data costs a lot of money. If you can do it all on a big scale using machine learning, then you can potentially save a lot of money. So to process lots of data, you need a lot of CPUs. So distributed data processing is often used by these large-scale internet applications, such as commercial websites. I mentioned Facebook, Google, Amazon, these kind of people. And it is itself a form of large-scale internet application, as I'll explain with things like Boink and the cloud data processing farms. So in this lecture, I'm going to give a little bit of a skim through the different kinds of hardware that have been used over time for the various kinds of parallel computing. Hardware and software, and then I'm going to talk about how we can actually measure the benefits of distributing the data processing over multiple machines, Amdahl's law and Gustafsson law. Then I'm going to talk about a sort of paradigm that emerged fairly recently, the last sort of 10 years or so, called MapReduce. And this is a way in which you can, it's really just a way of thinking. It's a way of splitting up problems in such a way that you can distribute them across large numbers of CPUs in an efficient and easy way. And then Apache Hadoop's the software that a lot of people have been using to do MapReduce operations. And then there's a lot of stuff that's come out since then that's trying to improve on Apache Hadoop, maybe go beyond MapReduce and that kind of thing. So that's the idea. So I'm going to start with a little bit of a sort of stroll through the parallel computing landscape. So some of you may come across Moore's law, this idea that the number of transistors in a dense integrated circuit is doubled approximately every 2 years. So, you know, when I was sort of, you know, doing at university or whatever, you know, every year, every 2 years, there'd be like a new processor that ran twice as fast because they managed to pack everything more densely into a single CPU. So, you know, there has been this trend, and it used to be like the guiding manufacturers used to sort of use this to plan their development because they wanted to stick roughly to this. And the idea being that, you know, you have your, if you can double the speed of the processor, then people will buy a computer every 2 years to kind of keep up with this trend. So it's good for the manufacturers as well if they keep this going. That's Moore's law. And so this is a log scale, by the way, so it's doubling. It's not you know, going up linearly. Transistors are still shrinking. They're still spending a bit of money on this, but there's been shifts in lots of different directions. Firstly, we're going to encounter limits as we reach atomic scale. We're not going to shrink beyond a certain point because then the noise in the atoms is just going to mess everything up. And so there's been a move to more power-efficient architectures. It's been recognized that power efficiency is very important with computing, and a move to multi-core architectures in the cloud. So the speed probably hasn't increased that much recently, but the way in which you can more efficiently distribute things, and you know, now my desktop, you know, heaven knows it's probably at least 5 or 6 years old, but it runs, you know, plenty fast for what I need, and it's got like 6 cores, I think, something like that. So, and most laptops now have 2 cores, and it's just getting about more efficient ways of using, you know, the transistors that they've got, and having several cores running instead of a single core, and that's definitely the way things are going. So it's moving towards parallel computing, and is already a, you know, a successful example of parallel computing on a small scale. So, so another sort of big direction in parallel computing in the last few years has been towards use of GPUs. So this is a graphics card essentially, but a rather big fat one. And this is the NVIDIA Titan. So these graphics cards have like their own lots of processing cores inside them. Now they're not as powerful as the CPU, but you can still do a lot of useful computing on them. And because there's a vast number of them, you can actually do like a lot of parallel computing using them. So this NVIDIA Titan's got like 3,000 cores. And so if you can distribute your computing task across those cores, you can get some real significant speed up. So when I was at Imperial, I was collaborating with someone who was writing a neural network simulator on these that ran on CUDA, ran on GPUs, and it ran pretty fast. It could do 100,000, 200,000 neurons close to real time using the CUDA acceleration. So communication's fast within a graphics card because it's got like all this shared memory stuff you can use for the cores to talk to each other. And you can build these kind of fancy racks that have, you know, lots of these graphics cards combined. But once you get beyond this, it becomes a little bit tricky. The bandwidth goes right down. You've got a problem that, sure, you can run things lightning fast on one of these rigs, but when you try and run them across 2 of these rigs, it gets a little bit tricky. So this is exactly the problem we had in Imperial. So my colleague got everything running fantastically on one core, on one graphics card, and it'll do, let's say, 200,000 neurons in real time. But then trying to what if you want to run 1 million neurons? Then you've got to like write some kind of code that, you know, opens up sockets or uses some kind of message passing, and it passes all this over the Ethernet, which isn't that fast really if you want to do this all very quickly. And then you've got to efficiently partition the network so that you minimize the network communication. It all becomes really messy. So GPUs are great if you've got a task that fits on them. They're a little bit more tricky if you want to spread it across lots of different graphics cards. And to run things on GPUs, what you use on NVIDIA GPUs is called CUDA. It's a sort of parallel computing platform. So you can write code in C++, C, or Fortran, and then the CUDA will enable you to the CUDA libraries will enable you to distribute that computation across all the graphics, or across all the cores in all the graphics cards. And there's some third-party wrappers for the language. So, you know, there's a little bit of overview on CUDA, NVIDIA's homepage, and I think there's probably a library for Agea, is it, the other graphics card? So there's other libraries for this, but CUDA's the main one. Now, another approach to parallel computing is supercomputers, right? You just cram vast numbers of computers and RAM into like one single machine, a supercomputer. And, this used to be like the big thing, these enormous big iron supercomputers. Still very expensive and still used, but only for very specialized things where there's really no other option. So here we've got the Met Office supercomputer. It's got almost 500,000 cores, costs almost 100 million quid. So it's not for word processing at home, right? And I imagine they've got very high-speed communication within the supercomputer, which is its advantage, right? So you're getting over this problem of distributing things over multiple cores. You've got 500,000 cores there, and they'll have some pretty fancy buses, I imagine, for shifting data around so that the cores can collaborate very fast. We've also got these software libraries that can be used to run code across multi-core CPUs and GPUs, and possibly across FPGA, which are like special hardware boards. And they'll distribute the tasks automatically for you. So these are like OpenCL, OpenMP. So I think, I haven't used these, except very, very briefly, but I think the idea is that you mark the bits of code that run in parallel within your code. So you write your code, and then maybe there's some operation that's got like huge matrices, you've got a multiplier, something like that, and there's like 20 of them. So you can mark bits of code that are parallelizable, and then the library will automatically distribute. When it compiles it, will automatically distribute the parallelizable tasks across the CPUs or GPUs or whatever it's got available. I think, and it's a little bit like what I used when I was doing my PhD thesis. I wanted to run a neural network across multiple machines, and they had this thing called a parallel virtual machine, which isn't really used anymore. But again, the idea is you submit jobs to this parallel virtual machine, and the parallel virtual machine takes care of splitting those jobs across the different computers. And then we have cluster computing. So this is a Beowulf cluster. So Beowulf cluster is really just a bunch of cheap or bunch of standard commodity hardware machines. They're all running Linux, and then you're using the Linux tools to shift the data across and start the computations on different machines. And a lot of scientific work was done on Beowulf clusters a while ago. I said during my PhD, I had like my little mini Beowulf cluster of 2 machines, which I was distributing the jobs across, again, using the Linux shell stuff. And the idea is it's cheap commodity hardware, and it's rigged together to produce a more powerful computer, linked together with like Ethernet, something like that. So, the sort of server farms essentially evolved from this Beowulf cluster idea, and they sort of took out all the cases and sort of became a much more, used servers or whatever. But it's basically a way of rigging together lots of standard computers into a more powerful computer, or a computer you can just send lots of different jobs to. And then we've got shared computers. So BOINC and SETI at home are both topics for the essay and class presentation. So we'll be hearing much more about that from you guys in the autumn term, no, in the spring term, beginning of the spring term. And the idea here is we're using a spare CPU of home users. So if you switch on your computer at home, let's say you've got a 6-core machine like I've got at home, and you're just like typing an email, right? You're using maybe some fraction of one of those cores to type the email. So the idea here is that people at home who believe in science or are interested in finding extraterrestrial life or something like that, they donate the other 5.5 cores worth of their machine's computing power to some useful and worthy purpose, such as protein folding, finding aliens, or processing astronomical data. So that's the idea. So people are sort of donating the CPU time of their machines to be used for scientific research. That's the idea. And this enables researchers to tap into processing power of hundreds of thousands of personal computers. So that's what BOINC does. It's a framework that distributes jobs to volunteers, people giving their computers time, and then pulls back the results for really big processing computing jobs. So on the 14th of March 2016, I had a look at the page, and they've got like 300,000 people participating in this program. So it's a lot of machines, right? We've got like 5 million computers and about 12 petaflops. So you can get a lot of processing power by tapping into these into people donating their CPU time. So BOINC is probably one of the bigger ones of these things. So you have a client running on the user's PC. It downloads the tasks and the libraries required to execute those tasks, runs the tasks, produces these output files, and then these are uploaded to the BOINC server to check that there aren't any errors They run like the same task on two computers and check the results match. And you get this kind of credits, whatever that means. Maybe people can compete for, you know, how much they're donating to the scientific work. So I think, yeah, so there's BOINC, I think it's astronomy data, like telescopes, looking for stars, this kind of stuff. And then we've got the SETI at home, which is like looking for aliens. I don't know if they've found any yet. And then there's protein folding, because again, that's another heavy computational task, like calculating how proteins fold for like, you know, developing new drugs, this kind of stuff. And then we've got grid computing. So this is a sort of middleware sort of way of sharing computing resources, like again, between institutions typically. So you have a sort of super virtual computer consisting of many network loosely coupled computers. So, you know, maybe Leeds, let's say, spends £1 million on this like, you know, semi-supercomputer thing, but they're only using half of it. And so grid computing is a way of setting up fast network communications and all the middleware so that people across the country can share their big supercomputers, and then they can sort of collaborate. Then people on all the institutions can submit jobs to them, and they get executed in the jobs, and you get the results back. So geographically distributed existing computer resources are shared using the grid, and we're using software middleware tools, a bit like BOINC, to support the distribution of computations across the nodes. So this is the sort of idea. We've got the administrators, and then we've got the grid data show, and then we've got all the sort of big computers in the different organizations, and there's some kind of middleware and software that enables people to submit jobs to the grid and get the results back from the grid. And the grid itself is the different institutions' computers, typically quite big ones, that are doing the jobs for the users. It used to be popular. There's lots of books on this kind of stuff, but cloud computing's really taken over, I think. I mean, I wouldn't bother with trying to find out if Middlesex has a grid subscription or whatever. You know, I just use Amazon Computing Services. They've got vast numbers of server farms and some very nice services and software for doing distributed data processing on those server farms. And this leads us very nicely to cloud data processing. So here we have the model where, you know, we talked about in relation to data storage, right? We, instead of, you know, paying for our own CPU power, which if we're doing a research project and we need lots of processing power, well, we're going to need that processing power for 4 years. Does it really make sense to buy a whole new supercomputer to do all that processing and then, I don't know, put the teacups on it at the end of the project? Not really, right? It makes much more sense to hire CPU power for the duration of our scientific project, and then when we don't need it anymore, we can just we'll stop our subscription. And the same with companies, right? There's no point in a company paying all this money for CPU cycles for data processing when they're not sure next year whether they're going to need the same kind of amount of computing power or more or less or any of this. So it's much faster, much cheaper, more flexible to pay for CPU cycles in a server farm where they've got all these economies of scale. And they've also got economies of purchasing scale, they've got economies of administration scale, they've got cheaper electricity. It's like win, 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 really. So you can hire a virtual machine, such as Amazon Elastic Cloud EC2, Elastic Computing 2, whatever, Google Compute Engine, this kind of stuff. Or they've got all these kind of software services that can be used to process data in the cloud, such as Elastic MapReduce. Amazon has Elastic MapReduce, for example. So, you know, they've got a lot of trouble building this data center. Has 400,000 servers in it. So you can just hire a few of those for as long as you need them, rather than sorting out your own servers, installing Linux, you know. Again, during the PhD, right, what a lot of messing about to get my little mini Beowulf cluster of 2 Linux machines actually up and running and fully operational, you know. It took days, right? And then I still had all the administration aspects of it. And then I had 2 useless computers at the end of the project. So, you know, this is the way to go. And there you go inside. So you have, you know, large numbers of, in fact, I'm not even sure they've got boxes on these things. You know, they basically strip the computer down to the absolute minimum that it needs to have. You know, it'd be the CPU, it'd be a ton of RAM, and some kind of, you know, as much hard drive as they can get, and they can buy these things in vast numbers and so get very cheap ones, and then you can just use some of these for as long as you need them. And all the cooling's sort of built into the building, so, you know, it's all very nice, nicely designed. Okay. So that's a little bit of an overview on distributed computing. And now we're going to talk a little bit about how we measure distributed computing performance. Because the big issue, the big problem with distributed computing is that you need to be pretty sure that you're going to get more your job's going to run a lot. Right, let's start this again. So it's quite a lot of mental effort and time, and it's quite a tricky problem distributing a computation across lots of computing, lots of different CPUs. It's all very well in a single desktop where it'll just somehow miraculously run across multiple cores, and particularly if you've got a multi-threaded architecture, there's a good chance it'll sort of balance out somehow. But if you want to run something across 1,000 cores, to actually you've got to like split up your job in a way that will efficiently run on these different cores, and then you've got to send off the job to the 1,000 cores, let's say, pull back the results, and then integrate the results. And that'll work well for some kind of problems, and it'll work really badly for other kinds of problems. So some problems are nicely distributable, and so it's easy to write code that will actually distribute the job and get back the results. Other problems are just the sort of thing that you really just need to plod through the thing in a serial fashion, and you just got to spend as much money as you can afford on a very, very fast CPU. So to decide whether it's the sort of problem that really makes sense to send off to your server farm, or to send off to your cluster of 1,000 CPUs, or to write CUDA code for, we need to be able to measure the distributed computer performance. We need to measure and predict how efficiently we can distribute that computation, and that will help us to decide whether it's a good idea to distribute it. There's no point in distributing computation across 1,000 machines if it's not going to run any faster. If it's effectively just going to be running on one machine with the other 1,000 machines lying idle, you just wasted your time trying to distribute it. And here we have, so to measure the speed up, we've got a couple of laws. So we've got Amdahl's law, which is used to predict this, and we've got Gustafson's law. So I'll talk about Amdahl's laws first. So let's suppose that there's a program that takes a certain amount of time to execute on one CPU. And what Amdahl's law is how much faster is this thing going to be? How many times faster is it going to be if we run it on multiple CPUs? So it's the time for the program to execute on one CPU, and that's dead easy to measure, right? We can just measure it or estimate it just by running it on a single CPU. And then we can work out how long it's likely to take on multiple CPUs and get the speed up number. If the speed up's like 1,000 or something, then it's like, well, hey, let's run it on multiple CPUs, assuming it's a slow problem. If it's a trivial problem anyway, there's no point in going to the trouble of distributing it, right? So this is how we calculate it. So here we have three things. We've got the time taken to execute the task on one CPU. As I said, that's quite easy to measure or estimate. Then we've got the proportion of the tasks that can be distributed. So some problems are very easy to split up in parallel, and you can do that very efficiently. And there's just but there's still going to be, Amdahl's not going to be zero, because you've still got a little bit of overhead in terms of dividing up the problem and integrating the results and this kind of stuff. So if alpha's like 1, you're basically stuffed, because none of the tasks can be distributed. But if Amdahl's like quite small, then it's might be worth using multiple CPUs. And n's the number of CPUs got available. So I said, speed up's time for program to execute on one CPU divided by the time for the program to execute on multiple CPUs. So this is just t, this top thing. And then at the bottom we've got alpha t. So let's say alpha's, so say 9/10 of the task can easily be parallelized, and like 0.1 of it, or 1/10 can't. So in this case it's going to be like 0.1 times t plus 1 minus alpha. This is the parallelizable bit times t. So this is the time to take for the parallelizable bit to be executed, divided by the number of processes that we got to execute it. So this, if you sort of factor it out, you get 1 over alpha plus 1 minus alpha over n. So that's Amdahl's law, the speed up that you get by running a task on multiple CPUs instead of one CPU. So let's take a little example. Suppose alpha equals 0.25. So 1/4 of our computation just can't be split up in any way, and 3/4 of it can be easily parallelized. So then in this case, plugging in the numbers, we get 1 over 0.25 plus 0.75 over n. And so as n tends to infinity, as we get like 1,000,000 CPUs or billion CPUs, this number is going to basically tend towards 0. And so what we're going to get is our maximum speed up. However many CPUs we throw at this problem, our maximum speed up is going to be 1 over 0.25 equals 4. So this shows you that, well, in this case, because alpha's 0.25, it's probably not really worth spending all the time and trouble distributing across multiple CPUs, unless it's the kind of problem that takes a year to run. If it takes a year to run, well, hey, maybe it's worth making it run within 1 year rather than 4 years. But if it takes 5 minutes to run, well, you know, if it take, then who cares really? You know, we're going to save a few minutes, but it's not worth parallelizing it. Excuse me. So now so that's Amdahl's law. And Gustafsson sort of came along and said, well, Amdahl's law is all very fine, but really it's a little bit academic. I mean, it's like, it assumes that there's a single problem, and then we're running it on 1 CPU, or running it on 10 CPUs, or running it on 100 CPUs. But the real world isn't like that. In the real world, or even in the scientific world, what happens is the more CPUs we have, the more, you know, the bigger problems we tend to try and solve using distributed data processing. So if I'm running a simulation, well, let's pick an example. So with neural simulations, I know a little bit about that. So with a neural simulation, you have a certain time step. You might update your simulation every millisecond, let's say. And you might have a very simplified model of the neurons, that each neuron is just like a single point with a single like little sort of, whatever it's called, threshold function, whatever, running inside it. And then so each point in time, each millisecond of each millisecond simulation time, you just update the threshold function, or whatever, or the membrane voltage, and then for each of the neurons in your network. But if you and that's what you do and you do it in that way because you've designed the problem so it'll fit on the available computing resources that you have. Now let's say we have, someone gives me, 1 million CPUs to do the same problem on. Well, I'm not going to run the same problem much faster because I kind of fitted my problem to match my computing resources. If someone gives me 1 million CPUs to run the same problem, then I'm going to maybe increase the time step resolution to like, 0.1 of a millisecond, something like that. I'm going to add much more complex structures to my neurons and have a much more complex function, use Hodgkin-Huxley instead of some simple sort of, sigmoid function or whatever. And I'm going to make my neuron model much better so that and then I'm going to run my much better model on the available computing resources. So this is what I mean when it says the problem size increases with the number of processors. The more processors I have, the richer and more complicated the problems I try and solve with those processors. So people change the grid resolution, the number of time steps, the complexity of the problem, and other parameters to allow the program to run in a desired amount of time. Most of the time, the limiting factor is the time available, not the problem size. The scientist wants to get the result so he can go home for coffee, for tea, or whatever. He's not sort of having a fixed problem. He's hacking the problem to match the computing resources. But Gustafsson came up with a different law that reflects this more realistic situation. So what matters is the workload that you can do on a single CPU versus the workloads that scaled up to multiple CPUs. So you've got W and W dash, n's the number of CPUs, and alpha again is this task of percentages of tasks that can't be distributed. And Gustafsson's law is that the speed up is W over W dash, which works out as alpha plus 1 minus alpha over n. I'm not going to bother with the derivation now in this one. So suppose alpha is 0.25, so the speed up according to Gustafsson's law is 0.25 plus blah, 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 comes up to about 7. If we've got 10 processors, about 8. But in this case, if we throw 1,000 processors at the problem, then we're getting a speed up of 750. So by adding lots more, another 100 times more processors, we're getting 100 times more, roughly 100 times more speed up. So in Gustafsson's law, it'd be extremely worthwhile investing in those extra 1,000 processors because I'm getting much more work done. It's just the work itself will have changed slightly, but I'll be much more pleased with the results. So that's Gustafsson's law. Okay, so that's a little bit of an overview of distributed computing, I guess. And now I'm going to go into some of the second half of this talk. We're going to look at MapReduce, which is a very nice way of solving the problem of distributing the computation for a certain class of jobs. So we're going to look at MapReduce, and then we're going to look at some of the software that's been used to execute MapReduce jobs. And then we're going to look at some of the alternatives that have been emerging recently. So I hope I made clear by now that it can be a big challenge to write programs that run efficiently across thousands of CPUs. You've got the bit that can't be distributed, and then you've got to do all the messing about to get the thing to run across the CPUs in parallel. You've got to distribute the input data, and then you've got to pull back the results from all these machines and integrate them all together somehow. And so what MapReduce is an efficient way of thinking about how you can split the problem up and distribute it across multiple machines. And then there's this Apache Hadoop, which is the actual software that will do that for you. So if you can express your problem in a MapReduce way, then there's a good chance you can efficiently distribute it. That's the idea. So this is just a way of thinking about doing you're solving your problem. And this can be applied to like a really wide range of problems. So it's quite a generic thing, and I'll give you a couple of examples. So the sort of short picture, and I'm going to explain this in a lot of detail, so don't worry if getting it immediately. We take a set of input key value pairs. So this is a set of keys and a set of values. So remember all that stuff from hash maps and hash tables and the rest of it. So this is a bit like a hash map. We have a key, and for each key we have a value. A set of input key value pairs, and this outputs another list of key value pairs. It takes a key value pair, sorry. Each mapper takes a key value pair, and it outputs a list of key value pairs that are a bit different. And the reduce function takes a key and a list of values and produces another list of key value pairs. So you say, well, have we really gained much? But it's what's happened is we've transformed the data in such a way that this is sort of not very useful and that this is much more useful, and that'll become much clearer. So we've got three stages. We've got the map stage, the shuffle stage, and the reduce stage. So I'm going to say a little bit about each of these. So the map function takes a key value pair and maps it to an array of key value pairs. And these are like intermediate key value pairs, so the example will make it clearer. So it's often used to process data from a file or directory. So the key here might be the file name, and the value might be the data in the actual file. So the input files pass to the mapper function, and the mapper function processes the data and creates several small chunks of data. So that's these several small chunks of data here. Then we've got a shuffle stage, or a sort of group by operation, depending on how you talk about it. So why it's called MapReduce is a little bit unclear to me. It should be called map shuffle reduce or map group by reduce. Maybe it's just a little bit of a shorthand. But anyway, you have to have the shuffle stage. So I said the map takes the key and the value and produces an array of key values. The shuffle stage takes this array of key values, shuffles it around, as the name suggests, and produces a key and array of values. And then this key and array of values is then passed through the reduce function. So we've got the map producing the array of keys value pairs, the shuffle produces key and array of values, and the reduce phase takes a key and array of values and produces another array of key value pairs. And this output's stored in the file system. So it's merging. The idea of this is all merging, it's all a sort of merging and reduction process that's producing a smaller set of values from the initial starting set of values. So to give you a little example, so here's our sort of documents going to the mapper function, and they're producing, let's suppose, counts of letters. So this is got A1, B2, and the documents fed to this mapper. It's producing C3, C6, A5, C2, B7, C8. This is the array of key value pairs, A1, B2, blah, blah. Then we got a shuffle stage, which converts these key value pairs, lots and lots of key value pairs, into a key and a list of values, key, list of values, key, list of values. And then the reducer, in this case, is looking for the maximum. So the maximum sort of here is 5, so it's outputting 5. Maximum here is 7, and the maximum here is 9. So that's, and we're going to go through a much more detailed example. So this is the classic, how do you understand MapReduce? Well, you look at a word counting in document problem. So let's suppose you've got to count words in 1 million documents, right? So again, another job I applied for last year, which I didn't get, but this was a company that was trying to analyze scientific papers to make predictions about new drugs that could be developed. So new sort of pathways in cells and genes or whatever, and trying to apply machine learning to scientific papers to predict new drugs or new potential areas for scientific discovery. So that's what they're trying to do. And obviously they had there's heaven knows how many scientific papers are published in this area. That must be millions, potentially millions. So this would be, again, the sort of problem you could do with MapReduce, but this is a sort of simplified. So that's a real-world example. They're spending lots of money trying to solve this problem. But this is a sort of simplified problem, simplified version of that, but can easily be linked up to real-world situations. So in this case, suppose we want to count the number of words, and if we're doing, just another example, if we're doing digital philosophy or something like that, and we wanted to do some kind of analysis of philosophical papers to find emergent trends or something like that. Again, this will be exactly, we'd split the problem up and analyze it in exactly this kind of way. So in this simplified example anyway, we want to count the number of words in 1 million documents. So if we want to work through each of those 1 million documents on a single CPU, it's going to take an awful long time. It's much more efficient to split the task across multiple computers, and this is a classic MapReduce task. So if you look for MapReduce examples, this is the one you often get. So the map function, each mapper, we're going to give the document name and document contents. And what the map function is going to do is it's going to split the document into words. It's going to extract all of the words in the document and count the number of occurrences of each word. And it'll output a set of key value pairs in which the key is the word and the value is the number of occurrences of the word in the document. So the input to the mapper is a key document name or something, I suppose. The value will be the document contents. And the output is for each word, how many occurrences of the word there are in the document. So let's suppose in one document there's like 100 instances of the, 5 instances of cat, and 33 instances of fish. And so what the map function will output is like the 100, cat 5, fish 33. Like here's the key, and here's the value for those words in the document. It's a pretty, the catfish, cat, fish the cat. Yeah, not a very exciting document, I guess. So we have one map function processing one document, and it emits these 3 key value pairs. And then we have another map function processing another document. And let's suppose that this emits the 34, tiger 12, and fish 2. And all the other million mapper functions, or however it's worked out, will do exactly the same thing. And emit the word counts in each of their documents. Then we have the shuffle stage that combines these outputs from all the mappers into the 134, cat 5, fish 33, 2, tiger. So it sort of aggregates these outputs and merges them together. So we've got there's 100 the's emitted from the first map function, and we've got 34 the's. So the total the count, so it gets an array of these counts, like the 134, like a list of the counts that have been found in each of the documents associated with the key the, and the same with cat, fish, tiger, and so on. And then these outputs from the shuffle stage are then fed into the separate reducers. And if in a simple example, we're just counting the words, not doing elaborate statistics on them. So what we then do is we add together the values to get the total number of each occurrences of each word in all the documents. So the reducer has quite a simple job. It just takes for each key, adds together all of the values in its array. So it takes the 134 and produces the 134. And the same with cat, fish, 30 tiger. So in this way, with the map, shuffle, reduce, we're then getting the word counts from all those million documents, and that can be split up and distributed across as many computers as you've got in a very efficient way. And it can all be split up automatically using Hadoop, as I'll explain. So just to sort of ram the point home, I guess, let's have a little look at electricity data. So this is another example. So here's a bunch of electricity data. This is for whatever, for a house, for a city. I can't remember what this is from. It doesn't really matter. So here we have, like in 1979, there was like 23 units, 23 in January, 23 in February, blah, blah, blah. And what we want is the average electricity data per month. So we want the average of all these numbers in this table. In this case, this table is absolutely trivial. But if we wanted the average monthly consumption for the UK, then that'd be like millions and millions of data points, and it would take much longer to process. And what if we want to process that on an hourly basis to get some really nice detailed figures and make predictions about electricity consumption and so on? Then again, we're going to have to do that in an efficient way in parallel. So this is just a simple example, but obviously, as the amount of data would scale up, you increasingly want to use this kind of framework to process it. So in this case, the input to the map function is the electricity data for each month. So each mapper is fed the electricity data for January over all the years, February, and then another mapper function is fed the electricity data for February all the years. I mean, this is just one way of splitting it up. You could also split it. You could feed one mapper function the data for 1979, another one for 1980, another for 1981. It doesn't matter. It's just a different way of doing it. So in this case, we're feeding it, this one mapper has one column, another mapper has another column, and so on and so forth. So in this case, so you see 23, 26, 31 is this column here. So we feed one mapper the key, and this is the set of values, another mapper function this, and the set of values. And then each map function is outputting the average electricity consumption for that month. So in this case, the output is just the average. And so the mapper is taking the average of all these numbers here and just outputting average. We don't need the fact that it's January because we're looking for the global average here. So we got like 12 averages spat out from the mapper functions. Then we have the shuffle stage. It takes all these averages, combines them into a single key, an array of values. So this is the average, and this is the average for each of the months. And then finally, we have the reducer that can then take these list of averages and take the average of the average to produce the average, the overall average so this is the monthly average across all the years and all the months. So again, very nice way in which you can split up the data, do independent parallel processing on that data, and then combine it back into a single result. So if you want to do this, so once you've expressed your problem as a map-reduce problem, you then actually want to go off and execute your problem on an actual physical computers, right? So what we need is a map-reduce framework that will take our problem expressed as a map-reduce problem and do all the computations for us and give us back the result. And this map-reduce framework provides a file system that stores the input and outputs, schedules the tasks, monitors tasks, and re-executes the failed tasks. And we got various map-reduce frameworks. So we've got Disco, which I know very little about. So Amazon has their Elastic MapReduce service, so you can actually run your MapReduce jobs on the Amazon Computing Cloud, which is probably quite nice. I haven't tried it. And then we've got Apache Hadoop, which has been used by a lot of companies to do these kind of MapReduce jobs. And so I'm going to talk about Hadoop because it's had a lot of influence, even though, as I'll say at the end, it's now possibly becoming a little bit obsolete. So Hadoop's like an open source framework written in Java. It enables data to be stored and processed across clusters of computer. So it has its own distributed file system that operates across all the computers that are involved in the cluster. And the data is processed across this cluster using MapReduce. So in this case, so people are often used to run Hadoop across their own like Beowulf clusters, like sort of thing I showed you at the beginning, a bunch of servers running the company's headquarters, whatever. But now I imagine a lot of this is shifting towards the cloud, so you maybe use the Amazon Elastic MapReduce to be more sensible than trying to run your own Beowulf cluster, I imagine. So it's great. So Apache Hadoop has lots of advantages, right? It enables you can quickly write and test distributed systems. You can it automatically does all the work of distributing the data across the and work across the machines. It can detect and handle failures. If a hard drive falls over and dies, it can recover from that. And you can dynamically add or remove servers. So once you've got all your cluster nicely running, which is going to cost you a lot of time and effort to get it all running, I'm sure. But once it's all nicely running, you can just submit your jobs to it. It'll automatically distribute them for you and then give you back the results. And it'll do this efficiently if you can efficiently write your problem as a MapReduce problem. And so I had a little look at jobs, and so it looks like there's plenty of jobs in Hadoop. So all this kind of big data analysis kind of stuff, there's lots of jobs in that at the moment, and they're pretty well paid. So if you're interested in a job that's well paid and like this kind of stuff, then you're onto a winner, I reckon. Okay, so how do we run a computation with Hadoop? So what you do is specify the input and output files. So what's the system going to process for its input, and where's it going to put the results? Then we need some Java classes that implement these map and reduce functions, and then some parameters, to configure the job. Then we've got this Hadoop job tracker that does the work of distributing all the software, all the sort of input data to the sort of slaves or the machines that are doing the actual work. And then it schedules and monitors these tasks, make sure they're all running, and provides status and monitoring information to the user. And then we have actual task trackers. That's a job tracker. And then we have task trackers on different nodes that execute the actual MapReduce implementation. And then the output of the reduce function is stored in the file. So this is the one limitation of Hadoop, is that it's all based on storing and retrieving things from files, and that's because it was like the first successful version of this kind of system. And I'll talk about later about I think it's Apache Spark, which is using much more in-memory computations, which is much more efficient. So the Hadoop distributed file system's inspired by the Google file system, and it enables you to run a file system across. So on your hard drive or running Windows or whatever, you've got a file system that's used to store, and basically is an interface between the ones and noughts on the drive and the actual operating system, so you can store and retrieve files, and it calls a record of files. You can store your documents on the files and so on. And this is like a distributed file system. As a file system runs across lots of different machines, so you just store your file across those machines using this file system. So the Hadoop distributed file system will run on thousands of computers in a reliable, fault-tolerant manner. It's got this master-slave architecture, so you've got a sort of name node managing the file system and then data nodes storing the actual data. So again, it's a little bit like BitTorrent, right? That you've got the tracker computer and then the other computers that actually hold the data. And so to store it, you split it into several blocks. These blocks are distributed across the data nodes, and then you've got this name node that's controlling the whole thing, determining the mapping of blocks to the data nodes and the replication of the blocks across data nodes to handle failures. So we've got this master server called the name node that manages the namespace and regulates the client's access to the files, and it does all the file system operations such as renaming, closing, opening files, directories, and so on. And then the data nodes actually hold the data. They hold these chunks of data, and these chunks of data, are sort of all the records of the files are stored in the name node, and then the data nodes actually hold the data, and and the name node tells the data nodes how to, the rules for creating blocks, deleting blocks, replicating blocks, and so on. So it's pretty straightforward, really. We've got the client, and the name node holds all the records for the file system. So these data nodes don't know much about what's going on, but they're just told to sort of store data, store a block of data, or to replicate a block of data, and so on. And so the client gets the information about the files from the name node, and then actually reads and writes the data to and from the data nodes. And that's all nicely coordinated by the Hadoop distributed file system. And this is important so that you can write the input files to the distributed file system, and then the code that's actually executing those jobs can then pull the data that it needs from the file system. So Hadoop itself is really designed for Linux, because then it can use things like SCP or SSH to kind of move files around and access different parts of the cluster. So again, that's why it's classic sort of Beowulf kind of architecture. It can run on Windows using CGWin. You may have come across CGWin. That's like a sort of way in which you can run lots of Linux programs like the shell and so on Windows. It's like a sort of set of libraries that enable you to do that. But it's not fully supported, and I thought initially I'd get Hadoop running and show you a nice little demo with a bit of code, but then it's just like, setting up my own Hadoop cluster just for the sake of demonstrating it seemed just a little bit too much work, so I didn't manage to do that. So that's Hadoop. And then on top of Hadoop, we've got Pig, Apache Pig. So I guess you guys must know about Apache, right? It's this sort of big software foundation, manages these open source projects. Anyway, so Apache Pig, high-level programming language that's used to create MapReduce programs run Hadoop. It's a simple sort of way of scripting Hadoop jobs without going down into too much of the messy details. So you have this thing called Pig Latin, which makes it pretty easy to write parallel code, can be easily optimized, and you can sort of extend it if you really need to. So if you're interested in this sort of stuff, have a little look at have a little look at that link. And so I have no idea about Pig Latin myself, but this is a simple way in which you can do the word count in Pig Latin. You have these sort of commands, and you can you can basically express a MapReduce job in a simple, compact way. We also have Apache Hive, and this is a sort of data warehouse infrastructure built on top of Hadoop. So it's a bit like in a regular standard desktop computer, you're going to have your hard drive and the actual physical chips or whatever, drivers, blah, 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 that enable you to manipulate ones and noughts. And then on top of that, you've got a file system like exFAT or, I can't remember the other one used in Windows, but whatever, exFAT example. So you've got the file system sitting on top of all the drives and stuff, and then on top of that, you might have a database running, right? You might have SQL running, like a MySQL or Oracle database, something like that, which then lets you store data in this organized way using tables and so on. So Apache Hive is a little bit like a sort of database that's built on top of Hadoop. It's initially developed by Facebook. It's currently used and developed by Netflix and FINRA. I think it's some kind of financial regulation authority. And Amazon uses Apache Hive in its Elastic MapReduce web service. And this enables you to query and manage large data sets that are residing in distributed storage, so you can manage the data much more easily and effectively using Hive. And so it works sort of in combination with Hadoop distributed file system and also with Amazon S3. And it's got a sort of SQL-like language like HiveQL, which lets you presumably store, retrieve, and search for data and so on. And so you've got a compiler that converts these HiveQL statements into MapReduce text or Spark jobs. So you can actually use it to create MapReduce jobs, I think. But again, I'm not an expert in this. So, and then we have, instead of Hadoop, you might want to use Amazon Elastic MapReduce. It's a managed Hadoop framework that lets you distribute and process vast amounts of data across dynamically scalable EC2 instances. And it'll also run a Spark, which is the sort of successor to Hadoop. So a little bit on that there. And you've got your student educate accounts, right, from last term. So if you want to play around with that, you're more than welcome. So beyond MapReduce. So, on Wikipedia article I first started to look at for this stuff, it argued that, there was some discussion about MapReduce and some links to some stuff where people are arguing that MapReduce has little novelty and performs worse than database management systems. And I think that's probably a fair criticism. I think if you're some kind of database whiz-kid kind of person and you spend enormous amounts of time thinking about your problems and writing very beautiful code that parallelizes them, and then you use like OpenCL or CUDA or something to process that, you can probably get the thing done much more efficiently. But it's going to take you an awful lot of time, and you've got to be very, very clever, right? So with MapReduce, it's a layer of abstraction. It lets you, once you've understood the MapReduce way of doing problems, you can then do lots of problems in the MapReduce way, and instead of writing all the code yourself, you can just use Hadoop to run those jobs themselves. So yes, maybe it has little novelty and performs worse than database management systems, but you've got to put an awful lot of work into getting a database management system to run as well as MapReduce, and even more work to get it to run better. So it's a great way of thinking about, it's a new way of thinking about parallelizing problems, and that's why it's become so popular, because it's fairly easy to do once you get the hang of it. Google stopped using MapReduce as well. They used to be big users, but then they were like, once you get to a few petabytes, it just breaks your mind. It's too cumbersome, can't be bothered, and they've got their own stuff, which I'll talk about. So yes, if you've got a few petabytes, maybe again, maybe it's not worth bothering with Apache Hadoop, and fair enough. And Google, can do what they like really, and they've got the resources to do that. So one of the successes that would be worth thinking about if you're interested in doing this kind of stuff is Apache Spark. And if I was doing these kind of large-scale data processing, I'd probably look at much more carefully into Spark. So it combines SQL streaming, complex analytics, supports Java, Scala, Python, and R. So it'll run on top of Hadoop, or you can run it in the cloud. As I said, the Amazon Web Services will support Spark. And you can access lots of different data sources. So you can use Hadoop Distributed File System, but you can also use Cassandra, that I think that's a NoSQL database Apple uses, and S3, that's the Amazon file system. So have a little look at that there. So I think this is probably the way to go with this stuff. So it's 100 times faster than Hadoop MapReduce because it can run in memory, or even on disk. They've written it in a way that makes it much more efficient. And although it supports MapReduce, you can also do other kinds of tasks like SQL, machine learning, graph algorithms, and so on. So it's much more flexible, it's much faster, and it can manipulate streams of data. Another couple of systems that are worth mentioning is Storm and Kinesis. So the idea here is that they've built these large-scale systems that are capable of processing and analyzing streaming data. So if we're talking about Internet of Things, which we're going to cover in the next lecture, then you might have lots and lots of data coming from electricity meters, say, smart meters throughout Britain, say, and this data is just pouring in, and then you need to process it as it comes in an efficient way. So there's Apache Storm, which is one approach to this, and Amazon Kinesis, another approach to this. Then we've got TensorFlow. This is a different way of thinking about how to do computations. This is sort of just a library for numerical computation, and the clever thing about it is it's using these data flow graphs. So each of the nodes in the graph are mathematical operations, and the edges represent these data arrays or tensors that are being passed between them. And TensorFlow is sort of written in such a way that once you've expressed your problem as a TensorFlow graph, you can then efficiently distribute it across lots of different devices. So the idea is that you've got here your data, and the data is sort of going into a computation and coming out of a computation, and then going into a different computation, coming out of a different computation. And presumably, this is parallelizable because you can maybe split up some kinds of data, and because you can split up these across different CPUs as well. So this is a slightly more complex sort of data flow thing, TensorFlow graph. So, again, this is a sort of a way of expressing your problem in a way that the underlying software can then easily map it across lots of different CPUs. And so Google has created their own cloud data flow that can be used to process these data, perform these data processing tasks on any size. I imagine it'll work on a vast scale, given Google's infrastructure. You'd have problems, slowing it down, I imagine. And then you've got this software development kit that lets you write a program using this data TensorFlow stuff to write a program that carries out your data processing job, and then the Dataflow service will execute that across the Google Cloud services. And soon it's moving into an Apache project as well. It's going to be called Beam. I don't know, it may have already moved. And you've also got Google's other nice sort of software libraries for this kind of stuff. So we've got this Google Prediction API, so pattern matching and machine learning API. So you can like bung a load of data in it and analyze it for you. You might get complete gobbledygook, or you might get some very sensible stuff as well. So there's a couple of books in the library, as well as a section in one of the course books. I haven't looked at these, but they might be of use. Okay, so just to wrap it up, in this lecture I've given an overview of distributed data processing, which, as I said, is often used by large-scale internet applications, and the data processing frameworks, like some of the bigger Google ones, are themselves part of or independent large-scale internet applications. So next and final lecture, I'm going to talk about the Internet of Things.